to question 7 of Higher Maths Paper 1, Leaving Cert 2008. Part A. Differentiate 2x plus sine 2x with respect to x. The only hard thing about this is knowing how the sine of a double angle is differentiated. This seems trivial, especially considering that later on in this question we're going to be asked about the a lot harder inverse sines. Anyhow, we'll apply the chain rule to the sine part of this problem because it's good practice for part C of this question. The chain rule is something that should be learnt off, but it's relatively short. There we have it. We have a function g, which is a function of f, which is a function of x, and what we do is we differentiate g with respect to f first, and then multiply it by the differentiation of f with respect to x. Along with the chain rule, we usually have to do some substituting. So in this case, let's call f of x 2x. This is overkill really, as 2x is too simple a function, but as I said, it's good practice for part C, which will be a lot meatier or crunchier if you're a vegetarian. So we can work out that the second term in our chain rule is 2. So we get d of g of f of x dx equals 2 times d of g with respect to f. Now, differentiating sine theta should be standard knowledge. For angle theta, it's cos theta. So our chain rule can be completed as 2 times cos of 2x. And knowing how easily the first term in this problem, 2x, can be differentiated, we can write out the answer now as we differentiate 2x plus sine 2x with respect to x, and we get 2 plus 2 times cosine of 2x. And that's our answer to this first part, A. Okay, the equation of a curve is 5 times x squared plus 5 times y squared plus 6xy equals 16. Find, differentiate it in terms of, find dy dx in terms of x and y. Having seen the chain rule in action, we get a chance to use the second of differentiation's key rules, the product rule, in this problem. It concerns differentiating two functions as they multiply each other, as in, and there is our expression of the product rule for differentiation. So we differentiate f with respect to x first and multiply it by g of x. Then we differentiate g of x with respect to x and multiply it by f of x. It's the third term in this problem that we'll apply this to. So the third term, as you see, is 6 times x by y. So we'll set f of x equal to 6x and g of x equals to y. And it's clear that this becomes then 6 times y plus dy dx by 6x. So that's our third term carried out. The chain rule can be applied to the second term, which is 5 times y squared. So we can differentiate the whole expression now as 10 times x plus 10 times y by dy dx plus 6 times y plus dy dx by 6x equals 0. The constant term 16 differentiates to 0. So all we need now do is rearrange the equation. And the two terms with dy dx can be grouped, while the other terms are brought to the right hand side. And then the dy dx can be isolated by using some algebraic division to get the answer as, and there you have it. That is our answer to section A of this part. So the same equation, there's a second part to this, to part B. We're actually given 2 points, 1, 1, and 2, minus 2, and we have to show that the tangents at these points are perpendicular to each other. Okay, we've got dy dx already. We can work out the slope of the tangent lines at any point from this. 2 points are specified in the question, and it's a case of substituting the values in. It happens like so. So in the first case, dy dx at 1, 1, we put 1 for x and 1 for y into our recently discovered dy dx, and we get minus 1. Then for point 2, minus 2, again we do the appropriate substitutions, taking care that on the denominator the y substitution occurs first. Easy to mix that up. And in actual fact we get plus 1. It's a fact that two perpendicular lines have negative reciprocal slopes of each other, and that's the case here with 1 and minus 1. So that's the question answered. The two tangent lines are perpendicular. So now we move on to the meatier or crunchier part C. So we're given inverse sine of a complicated argument in the middle there, x over the square root of 1 plus x squared, and we have to differentiate it with respect to x and produce a certain form. Okay, this is the trickiest part of the question. However, we can solve it by carrying out 4 things. The identity for differentiating the inverse sign, the chain rule to separate differentiation of the inverse sign and its argument, the quotient rule to differentiate the argument itself, the chain rule again to differentiate the denominator of the argument, that's the square root of 1 plus x squared. Okay, that might look like a tall order, but if we choose some letters in order to substitute functions, we'll be okay. So let u of x equal 1 plus x squared, so that when we differentiate with respect to x, we just get 2x. Then we let v depend on u and say that it's the square root of u, so that we can apply the chain rule here, okay, where we've already got du dx in our first point. So dv du then is a half times u by to the power of minus a half, and then we multiply by du dx, which is 2x, and so we get 2x all over 2 times the square root of 1 plus x squared. With these two operations, we have the denominator of the argument of the inverse sign already differentiated. To get the whole argument, we need to turn to the quotient rule, which is this expression. That should be recognizable, and also it needs to be in your memory. We set the whole argument to be a function w depending on x and v, and can say that the quotient rule would give us as given. So dx dx, which is trivial, multiplied by v of x, we've already seen that it's the square root of u of x, and we've given u of x as substitution, and we subtract that, it gets subtracted by x times dv dx and all over v squared. So now it's a question of making the substitutions that we've created, and we get that expression. Noticing that v turns out to be the square root of 1 plus x squared, and if it's squared, the denominator, we can see a potential cancellation of the square root and the square power occurring there. So we can go ahead and simplify, so that dw dx equals the first term, which is the square root of 1 plus x squared, all over 1 plus x squared. That looks nice. And then that has to be subtracted by that expression there. So we simplify further, which is possible, and having reached that expression, it can now be used in the following new way of expressing this problem. Okay, which is where we're going to apply the chain rule to the inverse sign itself. Because we worked dw dx out already and tried to simplify it, now we have to work out what is in fact the differentiation of the inverse sign. We need to know the identity for differentiating the inverse sign. This needs to be memorized. Okay, and it's as given. 1 over the square root of 1 minus w squared if w is the argument of your inverse sign. Okay, remember that w itself is the original argument of the inverse sign, and substituting we get that expression, and we can start simplifying. Notice how the denominator starts simplifying quite a lot, and we get 1 times, or 1 over, the square root of 1 over 1 plus x squared, which in actual fact is the square root of 1 plus x squared. So dy dw has turned out to be fairly simple. So the only thing that we have left to do now is to multiply this by our previously found dw dx, which is at the top of this slide, as you can see, and then we'll be finished. It's been a long trek, but convenient cancellations continue to help us. So we're applying the chain rule. We have to multiply the square root of 1 plus x squared by our previously found dw dx, and we get that expression, which simplifies to 1 minus x squared all over 1 plus x squared, which is 1 over 1 plus x squared. And this is the form a over a plus x to the power of b, the question required, with a equal to 1 and b equal to 2, which are both elements of the natural number set. So, thanks for hanging on in there.